looking at this compact electric ski system. It uses a water-resistant lithium-ion battery pack mounted on each ski, offers a claimed range close to 10 miles per charge, and reaches about 20 miles per hour in favorable conditions. The pair of motors produce around 25 Newton-meters of torque and drive short snowmobile-style treads that extend behind the skis. Total motor and battery mass is about 21 pounds across both skis. Each drivetrain module can be attached or removed, and the operator controls throttle, braking, drive modes, and battery information through a wireless remote integrated into a ski pole handle. From a neutral point of view, the machine operates as an electric aid that blends gliding with powered travel. It functions somewhere between cross-country movement and light mechanized support, giving the user a way to cross flats and moderate climbs without abandoning the feel of skis. The tread sits behind each ski on a 4-bar linkage and coil-over shock, allowing the propulsion section to keep contact across shifting snow surfaces without abrupt motion. When the drive units are switched off or removed, the skis act much like touring models, which helps during descents or when conserving energy. This dual nature is one of its strongest technical traits, since it allows a single platform to switch roles during a trip. The control interface on the pole keeps inputs close at hand, so the user does not need to reach for the skis during motion. Its price seems a bit pricey though. Say $3,000. Next, a vehicle that can move on both pavement and rail. It carries a 40,000-pound hook lift able to handle 20-foot containers, swap bodies, and industrial bins. It meets highway and rail standards and can shift between the two modes in under 2 minutes. It runs with a human driver today, and its platform supports future supervised autonomous control safety elements include rollover protection and rapid access points. Its power system follows the company's hybrid approach, supported by a fuel-flexible range extender. Reported performance figures point to cost reductions of 30 to 40%, 2 to 3 times higher use of existing rail lines, and emission cuts of 60 to 75% per ton-mile. On pavement, it moves like a standard container truck, traveling to ports, yards, or industrial facilities to secure a 20-foot container with its hook lift. At a rail access point, it lowers rail wheels, aligns with the track, and completes the shift into rail mode in less than 2 minutes. Once on the track, it proceeds to its assigned siding or transload location. Its hook lift allows direct placement of containers onto rail cars or into facilities without involving forklifts or hostler trucks. After unloading, it can switch back to pavement mode and continue to another task or reposition as needed. Because one platform performs both road travel and rail movement, it cuts delays and reduces the number of machines normally required at the first mile of freight transfer. This approach helps operators make stronger use of short line and industrial tracks that often remain idle. Moving more freight by rail, which offers stronger energy performance per ton-mile, supports lower emissions while preserving the reach of a road vehicle. Moving to system that links a motion platform, robotic camera crane, LED volume, and driving simulator through a unified digital twin built in Unreal Engine. The motion platform can tilt, rotate, and support cars, motorcycles, boats, or small aircraft. Each wheel rests on its own actuator, so suspension and tire movement look natural, and the platform can mimic anything from hard pavement to loose off-road terrain. Low latency keeps physical motion in step with the virtual scene. A robotic crane travels a 59-foot track and lifts the camera up to 24 feet. Its moves can be programmed, repeated, and synced with the platform and digital world. All crane commands pass through the digital twin for precise timing. The LED volume surrounds the vehicle with real-time environments. Lighting, reflections, and shadows react to both crane position and platform motion. Switching locations becomes a digital task, allowing fast jumps between very different settings without leaving the stage. A driving simulator lets a stunt driver record the exact motion needed for a shot. That data drives the platform, so crews can repeat the same action from multiple angles. Inside Unreal Engine, the digital twin mirrors the stage, helping teams plan vehicle paths, camera moves, and environmental settings before filming. The system runs on Unreal Engine 5.2 with development toward 5.5. Though based in Vancouver, the setup can be transported. Its strength comes from merging physical motion with real-time rendering so timing, lighting, and movement stay aligned, giving productions a controlled yet realistic way to film vehicle scenes. Let's be honest. Trying to control a VR world with regular controllers can feel like trying to play the piano while wearing oven mitts. Well, this glove turns the hand itself into the interface, letting natural finger motion register directly in virtual space. Once on the hand, the technical side comes into play. Each glove weighs about 45 grams and uses a sensing layer close to 1.3 millimeters thick. The fabric blends Lycra with a flexible polymer sheet that moves with the fingers. Inside that layer sit 12 elastic sensors that track up to 15 finger joints depending on the version, while other listings mention 21 joint angles or a 42-point angle layout, reaching around 0.01 degree precision. Latency stays near 10 milliseconds, and the sampling rate reaches 120 Hz. Wireless communication runs on a 2.4 GHz link with a range of roughly 16 feet. Power comes from a 760 mAh battery that offers about 10 to 15 hours of use, with a charging time close to 2 hours. The glove fabric can be hand-washed once the electronics are removed. It works with Steam VR, MetaQuest through PC or Link, and HTC Vive, and there is SDK access for technical projects. Functionally, the glove reads continuous finger motion and forwards those signals wirelessly to the VR environment. Because the material bends with the hand instead of resisting it, the sensors stay aligned and respond to small gestures. Many people are confirming that they can type or hold a glass while still wearing the gloves, since the material does not interfere much with routine movements. Next comes a lifting technology built around vacuum lifters, hoists, and support structures that move goods with less physical effort while keeping handling accurate and predictable. The range starts with vacuum lifters that move up to about 595 pounds using ergonomic handles that work in either hand. High-frequency units generally support loads under 145 pounds, offer a stroke of roughly 68 to 72 inches, and reach lift speeds close to 3 feet per second. Panel handling units move flat materials around 400 pounds with a pneumatic vacuum source and a tilt of about 80 degrees. Mobile vacuum units for order picking or trailer unloading lift roughly 176 pounds. Telescopic unloaders in the 88-pound class provide lift tube lengths near 98 inches and strokes close to 64 inches. Lifting trolleys support about 551 pounds and allow rotation or tilt of goods. Wire hoists handle around 265 pounds, while chain hoists reach about 5,512 pounds. Overhead and jib crane structures provide the mounting framework. The system works through controlled vacuum or mechanical lift force, letting operators guide items without heavy strain. Suction feet match the shape of boxes, sacks, sheets, or panels to keep grip during movement. Stroke length and lift speed affect how quickly and how far goods can be positioned. At PostNord's terminal in Jönköping, 13 units support parcel flow. About half are high-frequency lifters or telescopic unloaders. Workers there report less tension in their arms and shoulders during long shifts. Few underwater vehicles place so many people behind a single transparent boundary, and that alone gives this submersible an unusual presence. It carries a pilot plus 8 adults, all inside a large free-form acrylic sphere shaped through the manufacturer's Avier method. This structure creates far more interior volume than earlier dual-hull models of similar footprint, giving passengers wide-open sightlines and uninterrupted views in every direction. Its operating depth reaches 656 feet, supported by a 57 kilowatt-hour main battery that provides about 12 hours of activity. Movement peaks at roughly 3 knots. Power distribution comes through a dual 24-volt supply with an emergency backup. It carries both passenger compensation ballast and variable ballast of 550 pounds each. Propulsion uses 4 main thrusters and 4 maneuvering thrusters at 5 kilowatts each. Visibility outside the hull is supported by multiple LED units, producing 20,000 lumens apiece. Control inputs come through a joystick, touchscreen, and manual fallback. Next one. At about 6 feet tall and 3 feet wide, this unit produces up to 1 gallon of fossil-free gasoline per day, while removing around 10 kilograms of carbon dioxide from the air during continuous operation. The fuel reaches an AKI near 90, which corresponds to roughly 95 RON, and the catalytic setup can push the number higher. The gasoline contains no ethanol, sulfur, heavy metals, or fossil carbon, and it works with existing engines, pumps, and storage systems. People. The technology starts from a simple premise: pull carbon from the air, combine it with hydrogen split from water, and turn those ingredients into a fuel that behaves like conventional gasoline. The company behind it, founded in New York in 2019, structures the process around 3 continuous stages that link together without the need for crude oil. The first stage draws ambient air through a chamber containing a water-based solution with potassium hydroxide. As the air moves through, the solution captures carbon dioxide. Once saturated, the mixture is regenerated, so the captured gas can be extracted and the solution reused. The second stage splits water into hydrogen and oxygen through electrolysis powered by renewable electricity. The hydrogen becomes a feedstock for the next step, while the oxygen is released. This cycle refreshes the sorbent solution used in the air capture stage, keeping the system running without additional chemical input. Analyzing next, a mobility robot structured around a dual locomotion system and a seat platform that stays level while moving across a wide range of surfaces. It weighs about 220 pounds, carries up to 300 pounds, reaches roughly 7.5 miles per hour, and offers a range near 21.7 miles. Its wheel track layout combines 4 independently driven wheels with suspension and a caterpillar system supported by 10 to 16 powertrain units. It handles forward slopes up to 15 degrees and backward climbs up to 40 degrees. Stair movement reaches about 30 steps per minute going up and 35 going down. It is powered by a 24-volt, 44.8 amp-hour battery. Its operating logic relies on sensors such as LiDAR and gyroscopes that read spatial information and guide how the chassis moves. On flat surfaces, it runs on wheels with independent suspension. When the terrain shifts, the unit can switch into a climbing posture or engage the tracks to maintain progress on slopes or steps. Mode changes occur automatically based on sensor input, though the user still directs motion through a joystick, app, remote, or wireless key. The seat works in tandem with the sensing system. Gyroscopic input helps the platform react to angle changes and keep the rider level while the base adjusts during climbs or descents. Its range of adjustments in width, depth, height, and tilt allows it to fit many body types and distribute weight across the frame without strain on one point. In daily movement, it crosses curbs, grass, gravel, and mixed surfaces without dramatic shifts in motion. Indoors, it turns within confined areas and deals with minor thresholds between rooms. As for the price, there was a sum of $4,000 for pre-orders, so the final price, though not publicated yet, it could reach the sum of $9,000. A modular electric pod is built to operate alone or connect with up to 4 others, creating a larger unit with the capacity of an articulated bus or small tram. Each pod measures about 12.1 feet in length and uses an electric drive reported at a peak of 90 kilowatts. It runs on a 400-volt lithium-ion battery rated at roughly 47 kilowatt-hours. The structure is made mostly from steel, aluminum, and glass, and the company states that the materials are fully recyclable. Early data from the developer also notes potential reductions of up to 60% in CO2 emissions per passenger and up to 80% less traffic generation when used in modular pooling. Its technical core is the docking system. Pods can approach each other on regular city streets and connect through a robotic alignment method that handles the coupling while in motion. Once linked, the interior walkway lets passengers move between pods, which allows the system to reorganize routes without stopping. When the shared part of a trip ends, the pods detach and continue separately. The operational flow is built around on-demand mobility. A rider books through an app, and the system sends a single pod during quiet periods or a small convoy during higher demand. This flexibility gives it the behavior of a taxi, a microbus, or a cargo carrier depending on how many pods are active. The platform adapts capacity to real-time need, which may help reduce idle energy use and limit congestion. Although the specifications may evolve as development continues, the concept shows how modular electric pods can merge routing, capacity, and efficiency into one adaptable vehicle type. Veo 3 is a video generation model developed by Google DeepMind within the Gemini ecosystem. It converts text, and in some cases images, into short video clips with synchronized audio, including dialogue, ambient sound, and effects. The system supports 16:9 and 9:16 aspect ratios, offers 720p and 1080p resolution, and outputs at 24 frames per second. The publicly documented video duration ranges from 4 to 8 seconds. It includes a faster version, which reduces latency while maintaining the same visual specifications. The model responds precisely to user input, capturing details such as lighting, motion, camera angles, and style with improved fidelity. Compared to earlier versions, audio is generated as part of the process, not added afterward, allowing for a more cohesive result. Visuals and sound are produced together using a latent diffusion transformer architecture that merges spatial and temporal data with audio. In a single step, users can interact with the model through multiple platforms. It's accessible via Vertex AI for enterprise-level use, through the Gemini API for developers, and within consumer-facing apps, prompts are entered in English, and users can define aspect ratio and resolution to suit specific formats. It supports video generation from either a standalone text prompt or a combination of image and text, depending on access level. Preview features also allow the use of reference images or start and end frames for guided animation. These tools are especially helpful for rapid content development, such as short narratives, promotional clips, and concept planning. The technology includes safety mechanisms to reduce misuse risks, particularly with synthetic media. Veo 3 marks a meaningful step in automated video generation, with an emphasis on detail, structure, and multimodal synchronization. LG's 12-inch Stretchable Display is a next-generation prototype panel that LG Display has been showing at events like SID Display Week 2025, building on a technology it first announced publicly in November 2024. It's essentially a 12-inch micro-LED display that can mechanically expand by 50%, up to an effective 18 inches, while maintaining image quality. Therefore, a sheet of light that can grow from 12 inches to about 18 gives a clear sense of where flexible display research is heading. But this prototype uses a stretchable micro-LED system with a relaxed diagonal of 12 inches, a maximum 50% elongation, and an effective reach of roughly 18 inches when fully extended. This is a stretchable display that uses red, green, and blue micro-LED emitters, arranged at a density of 100 pixels per inch when relaxed. Each emitter measures up to 40 micrometers and sits on a silicone-based layer that behaves like an elastic film. This layer lets the panel bend, twist, fold, and bulge while staying intact, giving it behavior closer to a soft surface than a rigid screen. Its wiring follows patterns that open as the material extends, so the electrical paths keep their connections while the panel moves. Beneath the LED array is a stretchable active matrix backplane that delivers individual drive signals to each sub-pixel. This helps the panel keep consistent color and brightness even as its shape shifts. In practice, the panel serves as a demonstrator for future uses. It can follow the motion of clothing for potential wearable displays, adapt to curved interiors in vehicles, or take on roles in medical or industrial gear where visualization on moving surfaces is useful. It gives a clear view of what a deformable, high-resolution light source can do when mechanical freedom becomes a core design principle rather than a constraint. Next, looking to a curb-integrated electric vehicle charger that replaces part of the sidewalk edge, turning a standard curb segment into an AC charging point. This approach keeps the street layout unchanged while allowing a car to connect directly from the roadside without adding a standing column. The technical side centers on AC charging up to 22 kilowatts through a Type 2 connector in Mode 3. It runs on a 3-phase supply at 230 or 400 volts with 32 amps. Protection includes DC fault current detection, 2-stage surge protection, IP54 coverage for the full unit, IP68 for the enclosed electronics, and IK10 impact resistance. Its core feature is a sealed electronics module housed inside a concrete curb block. Some aircraft announce their purpose with speed alone, but this one behaves more like a test question given form. It exists to push through the parts of flight that many programs avoid, treating takeoff and landing at high wing loading as the main experiment rather than the prelude. The Quarterhorse MK1 is an uncrewed, remotely piloted research aircraft created to help map the path toward future high-speed and later hypersonic vehicles. Its role is narrow but critical. Gather real flight data during the toughest low-altitude phases, where aerodynamic limits close in and small control inputs matter far more than they do at altitude. The program sits inside a 4-step development sequence. The MK0 serves as a ground-integrated prototype. The MK1 handles flight operations near the runway environment. The MK2 is planned for lower Mach supersonic trials. And the MK3 aims to explore the hypersonic regime with a combined cycle propulsion system. This tiered approach allows each aircraft to examine a specific slice of the overall challenge, rather than attempting to solve everything at once. Only after this broader picture does the hardware take center stage. The MK1 uses a GE Aerospace J85 turbojet engine from the same family used in platforms like the F5 and T-38. Its airframe carries low aspect ratio wings and high wing loading along with a comparatively low thrust-to-weight ratio. This mix recreates the aerodynamic behavior expected in future high-speed concepts. Ground trials reached about 130 knots, which is roughly 150 miles per hour during high-power taxi runs. For more, the MK1 moved from concept to flight-ready status in 200 days, offering a clear look at how rapid iteration can accelerate a high-speed aerospace program. Up next, a cordless hard floor vacuum that centers on a narrow cylindrical body about 1.5 inches across and a total weight close to 4 pounds. Its fluffy cones head uses 4 conical brush bars that rotate in opposite directions, guiding strands outward so they do not wrap around the mechanism. Power comes from a hyperdymium motor with a 28mm rotor running near 140,000 RPM and producing roughly 55 air watts on hard floors. A 2-stage linear separation system captures particles down to 0.3 microns. The bin holds about 0.08 liters, roughly 2.7 fluid ounces, and compresses debris to stretch capacity. A magnetic dock charges the unit, and the handle's LCD screen shows mode, runtime, and alerts. The head includes LED lighting and can flatten to about 3.7 inches to reach below low furniture. Its slim handle lets the user guide it between chair legs and along edges without much repositioning. The conical brushes move debris towards the suction path while pushing long fibers outward, which helps the head keep turning on surfaces like hardwood and tile without frequent pauses to clear tangles. The motor's high speed gives the vacuum enough pull for everyday floor care, and the filtration system maintains performance as long as the filter is rinsed monthly. Although the bin is small, the compression system helps it remain usable for light to moderate debris before emptying is needed. During cleaning, the LED lighting highlights dust on hard surfaces, and the low profile helps it slide under shelves and sofas. The overall experience centers on precise movement, quick floor touch-ups, and effective pickup on hard surfaces, rather than deep carpet work. It costs about $700, differing slightly between countries and retailers. Imagine asking a coworker to jog beside you, listen to instructions, map the hallway, and keep its balance at the same time. This machine attempts something similar, and it does it with a calm, mechanical focus that never seems tired. It moves with a posture closer to human walking than what many humanoid platforms manage, keeps its legs relatively straight as it steps. That approach demands strong actuation and constant posture correction, fed by real-time sensor input. And the system shows it can hold this pattern even during an outdoor run, lasting about 4 minutes. Only after watching how it moves does the scale of the hardware come into view. The frame stands about 68.5 inches tall, weighs roughly 154 pounds, and uses an aluminum alloy skeleton with PCO ABS exterior panels. Arm reach extends to about 31.5 inches, and the combined thigh and calf length measures close to 37.8 inches. Movement comes from 42 active degrees of freedom. 2 in the neck, 7 per arm, 11 across the hands, 2 in the waist, and 6 per leg. It produces no less than 350 Newton-meters of joint torque and reaches laboratory speeds of about 6.5 feet per second. A 25 amp-hour battery, storing about 1.3 kilowatt-hours, powers the system for roughly 4 to 5 hours and recharges in around 3 hours. An 8-core CPU works alongside a 100 terascale per second AI processor to handle perception, planning, and interaction. The sensor array includes 3D LiDAR, 3 fisheye cameras, 2 depth cameras, and an omnidirectional microphone setup with speakers. Wireless links include Wi-Fi 6, Bluetooth 5.2, and 4G/5G. Software abilities range from voice interaction to face recognition, autonomous navigation, obstacle interpretation, map creation, OTA updates, and developer access. Controlling it is possible and actually quite fun, through a phone, tablet, or dedicated device. Its price: $120,000. This is a mobile training unit built on a cab chassis. It carries a 19,500-pound gross vehicle weight rating. It uses 2 full-length side doors and a rear door powered by electric actuators, along with a powder-coated front structure that shapes its stance. Optional wheel sets, tinted windows, and interior finish choices let operators adjust its look, and about half of the interior and exterior can display graphics or logos. Its equipment layout mirrors what many fixed gyms rely on. It includes 2 Torque dual cable towers, a Torque adjustable bench, a Concept 2 rower, a Torque Relentless rope trainer, a Torque Relentless Ripper ski erg, and band racks with a full band set TRX suspension trainers, 3 Torque Olympic barbells, a trap bar, and a BC Strength thruster light support, strength and conditioning work, a hinging squat rack with multi-grip pull-up bars, a rack system with universal shelves, a patented dumbbell storage system, and a medicine ball holder shape its main setup. It can support group formats of about 30 participants. Electronics feature a Fusion Audio Marine system with 8 6.5-inch LED speakers, 2 10-inch subwoofers, an 8-channel amplifier, and a touchscreen Bluetooth head unit. 2 42-inch smart TVs on the sides, and 3 27-inch screens at the rear, and cab area handle visual needs. A driver camera system, app-linked alarm, GPS tracker, and keyless entry support daily operation. It is powered by 4 200 amp-hour lithium batteries, a 600-watt solar array, a smart charging system with a 110-volt inverter, and a shore power or generator inlet. It even includes a compact office, includes a wood-top desk, cabinets, interior graphics, a refrigerator, USB ports, and 110-volt outlets, with optional climate control for trainers and operators running sessions or events. This is a foldable electric bike that uses a hubless front wheel and a mid-motor setup, placing it in a niche of compact commuter e-bikes with a distinctive mechanical layout. It uses a 250-watt mid-motor with about 65 Nm of torque, a carbon belt drive, and a single-speed setup. Its 36-volt 10.4 amp-hour battery sits inside the seat post and needs about 4 hours to charge. The listed range reaches up to about 46 miles, and the weight is close to 48 pounds. It uses a front V-brake and a rear disc brake, and the tires vary between puncture-resistant and tubeless high-grip types. The aluminum frame is described as fully recyclable. Extra elements include app pairing, a handlebar display, a USB port, and a battery lock. The hubless front wheel is the element that gives the bike its identity. Instead of a traditional hub, the wheel is shaped as a ring supported at the rim. This layout lowers the front mass slightly and creates a different steering feel. It also gives the bike a clean, circular look at the front. The frame folds through a 2-point hinge system that brings both halves together in one brief motion. This helps when storing the bike in tight rooms or placing it in a car trunk. The belt drive reduces upkeep because it avoids the metal contact and lubrication needs of a chain. With power fed through the crank area, the motor gives quick response when pulling away from stoplights or moving through narrow city routes. The seat post battery keeps the frame line simple and stays shielded within the structure. It slides out for indoor charging, and the display and app connection show speed, distance, and battery level without extra clutter. The price? $4,000. Further, representing an automated storage and retrieval system built around a cube of stacked bins and track-running robots. This platform uses a modular aluminum grid that can expand in length, width, or height, and reach about 22 feet at full clearance. Robots move along X and Y tracks above the grid, drawing roughly 100 watts while lifting, sorting, and delivering bins to operator ports. A common configuration reaches about 360 order lines per hour with 6 robots, while a single port often handles around 130 order lines per hour. The system stores inventory vertically instead of across aisles, which keeps items concentrated in a smaller footprint. Robots uncover the required bin, lift it from the stack, and bring it directly to the workstation, reducing the need for manual searching. Any port can receive any bin, so operators can pick and store at the same station without reorganizing stock. The software runs on tablets, connects through stable Wi-Fi, and links to ERPs, warehouse platforms, and e-commerce systems through an open API. A controller PC, UPS, and safety I/O hardware support the setup. Products that do not fit inside bins can remain on standard shelving, allowing a mixed layout. Because the frame is modular, operations can begin with a smaller footprint and expand by adding bins, grid sections, or additional robots as order volume grows. Further, a compact quadruped robot built for industrial inspection with a set of specifications that define how it moves, perceives, and operates, it weighs 110 pounds, measures 36.61 inches in length, 20.87 inches in width while each of its 4 legs supports a step height of about 9.8 inches and a gap crossing of about 11.8 inches. It reaches a top walking speed of about 5 feet per second, with a more efficient operational speed near 3 feet per second. It navigates corridors as narrow as 23 inches and handles slopes up to 30 degrees. The platform operates on a swappable 932 watt-hours lithium-ion battery that supports about 90 to 120 minutes of runtime and a range of near 3 miles under ideal conditions. A full recharge typically takes about 3 hours, with the battery reaching 70% in about 100 minutes. Its inspection payload includes a visual camera with 20 times optical zoom, a thermal camera that measures from -40 to 550 degrees Celsius, a pan-tilt head with broad vertical and horizontal motion, an acoustic and ultrasonic microphone with coverage up to 384 kHz, and a 360-degree LiDAR scanner. The robot functions as a legged inspection platform that navigates industrial environments where footing is unpredictable and access is tight. Its 4-leg structure helps it maintain stability on uneven ground, graded steps, and mixed indoor and outdoor surfaces. After a facility is mapped, it can follow preset inspection routes, position itself at designated measurement points, and avoid obstacles through onboard perception. Sensor data is collected with time and location metadata, which helps maintain consistency across repeated inspection cycles. The robot can transfer information through Wi-Fi or optional LTE and continues operating even if connectivity drops temporarily. The approximate price, $150,000. Some machines try to outsmart humans, but this one seems more like a calm partner that appears when tasks get heavy and simply shares the load without making a fuss. It uses powered hip and knee joints driven by brushless DC motors, with ankle movement handled by cables connected to motor units in the torso backpack. It provides powered help for hip and knee bending and straightening, as well as ankle push-off. The hips still allow passive side movement so the user can shift naturally. The frame can be adjusted through thigh and shank length changes, leg interface width and depth changes, a height-adjustable torso brace, and size-adjustable foot attachments. Pressure-sensitive insoles track force and center of pressure data. It has a backpack, holds a custom battery system with monitoring, plus mounting points for an SCBA tank. Its central idea is to move physical burden away from the wearer and into the ground through the suit's structure. Workers who handle heavy protective gear often deal with long hours of movement under substantial load, and this system aims to share that effort. The mechanical layout keeps the heavier components near the torso, while the cable-driven ankles transmit actuation downward without placing extra mass on the feet. The powered joints add positive work, so the user does not have to counter the system's weight or the mass of attached equipment. At the same time, the hips retain lateral freedom, so the user can shift side to side in a natural manner. Control software uses inverse dynamics calculations to determine the torque needed to counter gravity and ground reaction forces. Pressure data from the insoles allows the suit to adjust assistance step by step. Additional controllers support motions such as walking or lifting, and a classifier identifies activity changes so the suit can transition between modes. Sometimes a fire scene needs more than a hose. It needs something that behaves almost like a wind machine carrying its own weather system. This turbine-based unit starts with a 22 kilowatt fan inside an IP55 rated housing, powered according to user-specified electrical settings. It tilts from about -40 degrees to +40 degrees, rotates a full 360 degrees, and throws mist up to roughly 230 feet. Noise output stays under 93 decibels. Dry weight is about 1,605 pounds. Water flow ranges from around 92 to 634 gallons per minute, depending on the nozzle layout. Typical dimensions run between 70 and 76 inches in length, 85 and 98 inches in height, and about 51 inches in width. The system works by atomizing water into fine droplets that are carried outward by the turbine. These droplets absorb heat quickly because of their high surface area, which helps lower temperature in the fire zone and slows combustion. The same mechanism cools structures or open spaces, so it can handle both suppression and thermal reduction. Its mist can reach into irregular or porous surfaces more effectively than a focused jet, which helps in environments where fire sits beyond easy access. Electric tilt and rotation allow the operator to direct the plume remotely, keeping distance from hazardous areas. Built-in lighting supports use in low visibility. A compact steel frame houses the major components and keeps the machine stable during operation. Internal safeguards protect the turbine from overheating, and the platform can connect to automated detection or suppression systems when sites require coordinated response. Because the design is configurable, it suits large industrial settings such as ports, chemical plants, storage sites, tunnels, and mining areas, where long reach and consistent cooling are valuable. This is an electric bike with a frame that can change length. You can shorten it for tight city paths or stretch it for a calmer, more planted ride. Its power system centers on a motor that produces around 750 watts in continuous use and can reach peaks close to 3,000 watts. Torque lands near 180 Newton meters, giving strong pull from low speed. Riding modes set the pace, with limits starting near 15 miles per hour, moving to about 20 miles per hour, and reaching close to 30 miles per hour in the quickest setting. Energy comes from a 1,500 watt-hour pack, built from 21,700 cells, protected inside a metal case. The pack can be removed, locks in place when mounted, and uses fire-safe construction. Expect roughly 40 to 60 miles, depending on terrain, speed, and assist levels. Charging from 20 to 80% takes about 2.5 hours, while a full charge sits near 5. The wheelbase can shift between roughly 25 and 40 inches, which changes overall length from around 58 to 63 inches. When folded, the bike measures close to 44 by 37 by 21 inches for easier storage. Seat height stays low at about 31 inches, helping riders get on and off with minimal effort. It rolls on 20-inch fat tires using CST road rubber. Up front, an inverted air fork provides around 3.5 inches of travel. A 30-watt LED headlight with an angel eyes pattern handles night visibility. You're looking now at a hospital pneumatic transport network that moves carriers filled with items such as medications, lab samples, blood products, and documents. The tubes measure about 4.3 inches, 4.9 inches, or 6.3 inches in diameter, and a single carrier can hold up to 11 pounds. The travel speed can reach about 26 feet per second, and the layout can extend beyond 3,280 feet. Powerline technology allows up to 5 carriers to travel at the same time over long paths. The system supports auto return of empty carriers, carrier buffering during heavy traffic, RFID tracking, access control for sensitive goods, and optional HEPA filtration. Stations vary by location needs, including compact stations, multi-port senders, and ergonomic units with horizontal unloading. Carriers are made from strong polycarbonate and are available in standard, leak-resistant, and automation-compatible forms. The network replaces walking items between departments. A user places an item inside a carrier, closes it, selects the destination, and sends it. Airflow created by side channel blowers moves the carrier through tubes placed in ceilings, walls, or shafts. A central PC platform plots routes, handles traffic, sets priorities, and logs the movement of every carrier. At the destination, the carrier arrives at an accessible height, and certain stations require user credentials to collect sensitive materials. In high-throughput environments, such as large labs, automated unloaders can process hundreds of carriers per hour. Hospitals use this setup to speed movement of time-critical items and to support predictable internal logistics. It offers quick delivery, consistent routing, and clear traceability without shifting staff away from clinical work. These airborne platforms carry telecom and sensing equipment to higher altitudes while remaining linked to the ground through power and data tethers. Each unit relies on the aerostat autopilot, which controls ascent, station keeping, and retrieval with limited staff. The platforms are used for 4G and 5G coverage, IoT networks, fixed wireless links, emergency communication, surveillance, and long-duration monitoring. The ST Flex is the company's fast arrival model. It reaches about 1,000 feet above ground and supports payloads close to 132 pounds. The tether delivers roughly 1 kilowatt of power to onboard equipment. It can stay aloft for more than a week between helium top-offs. Its operational wind threshold is around 63 miles per hour, with tolerance up to about 93 miles per hour in harsher events. It is brought on a trailer-based station and typically completes setup within a single day. In telecom work, one unit can cover an area that extends roughly 25 miles from the launch point. The ST300 stays on site for longer spans. It carries up to about 660 pounds and operates near 2,000 feet. Payloads receive about 7 kilowatts of power through the tether. It functions in winds near 75 miles per hour. It is used for missions lasting weeks or months where continuous operation is a priority. The ST400, introduced in 2025, supports more than 900 pounds and can climb beyond 2,500 feet. It accommodates communications hardware, radar, EO and IR sensors, and counter-UAS payloads. A rail system enables quick payload swaps. Light outlining shapes on fabric can feel almost like a guide appearing in real time. And this system builds on that by projecting sewing patterns directly onto a 36-inch by 24-inch mat. The mat sits on a flat surface of at least about 37 inches by 25 inches, while a projector mounted on a telescoping beam sends the image downward. The beam fits between floors and ceilings from roughly 7.5 to 10 feet. Power uses common household ranges of 100 to 240 volts at either 50 or 60 Hz. Pattern transfer runs through Bluetooth and Wi-Fi, controlled with an app for iOS or Android. The package includes the projector, the beam, the cutting mat, pattern weights, a rotary cutter, target stickers that help with alignment, cord covers, and a power cable. Calibration is a regular task. Each time the beam or work surface changes position, the user takes a wide-angle photo of the mat with a phone. The software adjusts tilt and skew from that image. When working with thicker textiles like faux fur or Sherpa, the fabric can be placed under the mat during calibration, so the projection matches the height of the actual cutting setup. The digital library spans adults, kids, and accessory pieces. Many patterns include a 5/8" seam allowance. Mirroring is available for pieces that require a flipped partner, unless the piece is too large for a single frame. Large pieces trigger splicing. Red arrows appear to show the direction of the following segment. Stickers are placed on the first frame, and the next frame aligns with them to complete the full outline. Sometimes, a project in orbit feels a bit like assembling a model kit in zero gravity, and Haven 2 leans into that idea with a structure built piece by piece. It begins with clear physical parameters: a diameter of 14 feet, a length of 52 feet, 4,414 cubic feet of pressurized space, and 1,942 cubic feet set aside for crew activity. The launch mass reaches 63,934 pounds. 2 docking ports sit at its ends, and onboard supplies support close to 720 crew days. By 2032, the full station will become a large multi-module setup, with far more room for people and experiments than the initial unit. It supports a 12-person crew and carries the mass expected from a structure of that scale. Power capacity rises step by step as each piece arrives, moving from the output of a single module to the much higher level reached once the entire system is in place, with a clear share reserved for scientific work. The main structure keeps several standout elements: a broad cupola window for wide views, an EVA airlock for work outside the hull, a robotic arm for handling equipment, and external points where experiments can be mounted. Early modules fit Falcon Heavy, and a later, wider core unit is planned for Starship. Viewed neutrally, Haven 2 follows a method that lets the station grow at a measured pace. Each element adds room, power, and new attachment points for equipment. The expanded interior supports microgravity research, while the outside mounting points give instruments direct access to space. The development path will begin in 2028 and moves through a series of launches spaced roughly 6 months apart, as a successor platform to the aging ISS. A vehicle rolling into a bay and leaving only a few minutes later with a completely refreshed energy pack is the idea behind this battery exchange system. It operates through stations that can complete up to 408 exchanges per day and store as many as 21 packs on site. Each location includes a 2 megawatt-hour energy unit that helps manage power demand during busy periods. Compatible vehicles rely on uniform battery formats, such as the 75 kilowatt-hour pack. Another option, the 150 kilowatt-hour semi-solid state pack, announced the same year, reaching an energy density close to 360 watt-hours per kilogram. Every exchange is followed by automatic checks in the car to confirm proper attachment and electrical alignment. The sequence starts when the driver selects power swap mode within the vehicle system. Guidance directs the car to the correct station, where it enters a marked bay. The onboard interface, supported by the vehicle's assistant, helps position the car before the platform connects underneath. The station removes the depleted pack and installs a fully charged replacement, a process that may bring light movement and audible mechanical activity. After installation, the system verifies the condition of both vehicle and pack before allowing departure. In regions where battery as a service is offered, pack cost is handled separately, giving drivers the option to switch to a different capacity when needed. The overall method focuses on quick turnaround, mechanical precision, and consistent compatibility across supported models. Since a full exchange often takes under 5 minutes, it can serve drivers who prefer short stops or pass through areas with limited high-power charging options. Looking next to a reusable, hands-free shoe cover. It wraps around a shoe through a spring-driven action, measuring 16 inches in length, fitting footwear up to roughly a US men's size 13, and weighing around 150 grams per cover. The exterior uses polyester fabric with a polyurethane coating, and a thin metal core inside creates the opening and closing motion. Its upper surface resists water. The bottom has a textured pattern for grip on smooth floors, and it can be washed by hand. To use it, the cover is placed flat on the floor. The internal metal core holds it open. When someone steps onto the midpoint, the pressure shifts the structure, causing the sides to rise and wrap beneath the shoe. No bending or hand contact is needed. After stepping out, the cover can be pulled open again to clean or store. Its materials give it more substance than single-use plastic booties, and the coated fabric handles repeated flexing without breaking down quickly. The tread pattern on the underside adds stability when entering homes or offices, helping reduce slips on polished surfaces. The spring mechanism retains its shape through repeated cycles, which keeps the wrap action consistent. This type of cover works well in situations where shoes need protection before entering a clean space. Home service workers can move from a vehicle into an entryway without stopping to fuss with traditional covers. Real estate professionals can walk through showings without leaving marks on flooring. Inspectors who visit several properties in a day can reuse a single pair instead of carrying bags of disposables. A pair of it costs $29. And if you want to walk in the water, here is an interesting concept, but unfortunately you have to build them first. What are your thoughts about it? This is a drone that can shift direction without tilting and able to also move across a floor inside its own sphere, setting an uncommon starting point for an aerial platform made with Japanese materials. At its core, the device uses a cubic frame with 8 propellers, each on a different face of the cube. This layout gives it the ability to move forward, backward, left, right, rise, or descend while keeping its body level. Around the frame sits a geometric spherical guard that lets the craft roll across surfaces when flight is unnecessary, adding a second mobility mode that blends air and ground movement. Control comes from an algorithm that manages propeller speeds to balance the body while generating thrust along any axis. A compact orbital capsule that returns materials from low Earth orbit is unusual enough, but this one uses an inflatable heat shield that opens in space to almost 20 feet across. The capsule carries about 220 pounds of payload, while its own mass is roughly 550 pounds, resulting in a 1:2 payload to structure ratio. The company cites as far higher than common down mass options. It fits a 24-inch ESPA interface and measures about 4 feet 11 inches in diameter and roughly 3 feet 11 inches in length, which allows it to ride as a secondary payload on commercial launches. After reaching orbit, it completes a short mission period before a de-orbit burn sets its return path. Once separated, the heat shield inflates to form a wide drag surface that lowers the ballistic coefficient and cuts peak G loads to about 1/3 of those seen in classic rigid capsules. The large surface also supports guided descent without a parachute, with accuracy reported at nearly 10 times better than round cap systems. Atmospheric entry begins at roughly 25,600 feet per second before deceleration carries the vehicle to splashdown. Its first flight took place on SpaceX's Bandwagon 3 rideshare at an inclination near 45 degrees. It completed one orbit and splashed down about 1,240 miles off the Brazilian coast. Recovery did not occur because the trajectory shifted. A vertical lift cargo aircraft that flies without a pilot offers a different approach to medium load transport, and this model develops that idea through a hybrid system and autonomous control. It lifts on 8 Pipistrel E811 electric motors and moves forward using an internal combustion engine with FADEC that drives a pusher propeller. The electric components use liquid cooling, and an onboard management system tracks power flow and isolates faults when needed. The aircraft measures about 33 feet in length with a 43-foot wingspan and stands roughly 10 feet tall. Wing area is close to 248 square feet. Its cargo bay provides around 106 cubic feet of space at roughly 12 by 2.8 by 3.3 feet. Maximum takeoff weight reaches about 3,750 pounds, while typical payload sits near 660 pounds, with the option to trade weight for range. Trying to push a bicycle past highway traffic may sound like something a cartoon character would attempt. Yet this project treats that idea as a serious engineering challenge. It takes a familiar human-powered machine and wraps it in a shell shaped to slip through the air, with as little resistance as possible. The vehicle uses a composite body formed through vacuum infusion, a method chosen to keep the surface even and consistent. The shell comes in 4 sections that fit together in a long, narrow shape. The seam between these parts follows a curved path from the lower front wheel area toward the back, placed there to keep the air flowing smoothly along the sides. A small front intake brings in the limited air the rider needs while reducing disturbance around the nose. Inside, the rider lies on their back and pedals a chain drive that powers the rear wheel. The interior is tight, so the team chose a rider who fit the space while still being able to push strong power in this position. Earlier machines in this series usually ended up around 80 to 100 kilograms with the rider included, and this model stays in that general range, though exact figures were not released. The team began this version with the hope of improving on a previous high-speed run, and planned to take it to the World Human-Powered Speed Challenge in Battle Mountain. They had noticed that the earlier design suffered from unwanted airflow caused by a larger vent and a less effective seam location,